Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, today we will be talking about elements to constrain different degrees of freedom, and if you are talking about one translation constraint. So, usually what we have is articulated link with the ball ends, and along the longitudinal axis you have the constraints. So, this will be the general approach, and usually the notation is to show one constraint, linear constraint. We use dashed line with the one arrow. So, in this case, if it's along this line, so we can use the dashed line with the arrow. So, it's a constraint line, constraint direction, and one translation. That's how we are going to show. For one rotation, so what you see here is this is the direction, the rotation. So, for rotation we can use two arrows. So, or we can also say with the rotational direction. So, with the dashed line. So, if it's a dashed, it's a constraint. If it's a solid line, so suppose if it's a solid line, then it's a degree of freedom. If it's a dash, it's a constraint. Likewise, here also, if it's a solid line, it's dov. So, that's about the notation. So, if you want to constrain one translation, one of the way we discuss quite in detail is a point contact. And we can always idealize with the one spherical ball making contact with the flat surface here. So, that's we can always use, and dash line for the constraint. And another is, if we want to use the articulated links, we can also use articulated links. We can also use articulated links to show the constraint along the longitudinal direction. So, whenever we need to constrain translation, we can use these building blocks. So, either a point contact or a articulated link, or what we can also, we can use abstraction also. So, if you are using two bodies, so suppose spherical ball and the flat we have been talking about, and if this is the contact, what we also mentioned that we can use the constraint by just using a articulated link here. So, we will be learning about different designs, and one of the design to constrain one translation is also this kind of flexures. So, what generally we refer to is folded leaf spring, or many times we also call it folded sheet flexures. which we will be talking about later when we cover compliant mechanisms and flexures. So, for the time being, what we just remember that if we have to constrain one translation, we can always use a folded sheet flexures. In short form, we can call it FSF, and it provides constraint along the fold line. So, whenever we need to constrain one translation or to provide constraints, we can always place a folded sheet flexures such that the fold line aligns with the constraint directions. Another way is also using different sheet flexures. And this is how it should be aligned, so that the intersection of the different planes you can see 1, 2 and 3. The intersection line will be the constraint line, and again we can show using the dashed line with one arrow showing the constraint. So, this way we can also constrain one translation. Yes, coming to one rotation, if we want to constrain just one rotation, how to do that? Can we do just using some one element, or is there any building block? And what we realize that it's a difficult, and we always have to go via some kind of intermediate body. So, what happens when we use constraints in parallel? What happens? They constrain the rotation, but the problem is they also constrain the translations. And if we just want to constrain one rotation, we have to relieve or release that degree of freedom. So, if we just take this, the bottom, we can say C1 and C2, it constrains, it provides this translation constraint, and at the same time it also provides this rotation. What we want is only this. So, we need to release that, and how we do? So, we provide a intermediate body and go via intermediate body. So, and when we use another pair, what we realize that the intermediate body with the respect to the object of interest, which is the orange body, it releases that degree of freedom. So, if we just consider C3 and C4, and with respect to intermediate body, what we realize that it constrains the rotation, but it also constrains this translation. But what happens, since in this arrangement is in series, so any one DOF will release that degree of freedom. So, although it is a constraint in one place, it is a release in the other. So, therefore, we only get one rotational constant which is provided by both. So, if it is a series, it has to be constrained at both the places. So, this constraint, rotational constraint, we have in both the places, and that is why we can get one rotation in that plane. It can translate up and down, and in the other direction. since it is a thinner structure, so it can move easily. So, what we realize that in this case we will have only one constraint, and that is one rotation. So, there can be alternate arrangements, but here what you can see, the orange body is nested, is inside, but it is still constrained, the rotation is constrained with respect to the frame. And what we realize that again is via the intermediate body. So, the challenge is wherever we want to have just one rotational constraint, we have to use an intermediate body, and we can use this as a building block. And so, for translation we have articulated link, one articulated link, and for rotational constraint we can use this arrangement, and it constrains the rotation perpendicular to the plane. So, that we have to remember, and we have to use these blocks. What happens whenever we have this intermediate body, what we realize that the orange body, which is maybe what we can say is the body of interest, and is a constraint to the frame or to the machine base through the intermediate member. And of course, it constrains the rotation, but what we have to realize that the intermediate body is free to move. So, if we fix the orange body also, we do not have a control on the intermediate body. So, if we tap, it can start moving, and it has degrees of freedom. So, it can give a lot of problem in design if it is related to. So, suppose if you are designing something for high dynamics application or high speed application, then we may have to find a way to constrain the intermediate body also. And that is why was mentioned here that we have to be careful about this member. Yes, of course, one of the thing is the compliant members, the members what we are using here to constrain, they are very thin structures, and under tension they might be okay, but if there is a compressive load coming to these members, they are prone to buckling, and we may have to take care of that. Other is, since the intermediate body is suspended on these highly flexible members, so the stiffness can be very low, and we may encounter resonance, and that will also give rise to many problems. Fatigue is another issue. So, if it is a high speed application, because of the dynamics, because of the resonance, things can move very fast and the amplitude can be high, and the members may fail under fatigue. So, we have to be aware of these things and have to be careful while designing that. One of the way to constrain just one rotation is also using coupling. So, there are a lot of flexible couplings, and here is more like a bellow, and basically they are used for transmitting the power from the motor to the ball screw or to a shaft. And in order to eliminate any kind of offset or misalignment, we use coupling. But if you look at it closely, what we realize that these couplings provide very good rotational constraint, and that is the requirement we have when we design coupling. But we can also use the coupling in a way just to constrain one rotation only. Of course, there are some limitation, and that we can discuss when we talk about flexures, but in general it can be used to just constrain one rotation. Another thing to note is that it is not a simple component, it is a very complex component, and there are many features here we may have to be aware of while designing these things. Similarly, we can also use these couplings, and this can also provide the rotational constraint, this direction, and we can see the alternate arrangements. So, it's a slit, and there are alternate arrangements, and the thickness of the members are quite important, so that we can get certain degrees of freedom except the rotational part. So, if you want to build devices or mechanism to get certain constraints, we can just use the building blocks. So, for instance, if we want to just constrain two translations, so if we know the directions, so C1 and C2, along that we can simply put the articulated links 1 and then 2, and along the length we constrain the translation. So, we can just use these building blocks and can design different kind of constraint mechanisms. What we also realize that many of the flexures can be also used, and we can always use some equivalents. So, here is again sheet flexure with the hole. And what we realize in this case is equivalent to two translational constraints. So, if we just make it like this and opening, what we see here, because the dimensions here are really small. So, it can bend also. So, it is equivalent to just two articulated links connected in this way. So, we can have C1 and C2, and if it is like that, then we can also say that this can provide C1 and C2 constraints in that plane. So, it is a equivalent mechanism, and we learn that many times sheet flexures are used, and we replace a pair or arrangement of articulated links with the sheet flexures, and we can get very good mechanisms. And sheet flexures many times are preferred because it is easy to clamp them, and yes, it is very cost effective also. So, if you just check this, if you take these constraints, and we have two constraints here, two translation constraints, and what we realize that if we place them here, So, in 3 places. Yes, the orientation will be critical. So, we have to know that, but if we put it in a certain way, then we get 2C here, 2C and 2C, another 2C. So, total 6 constraints we can get, and we can get a very good kinematic mount. So, this is one of the application, and if we place any sensitive instrument or a plate where it is a very critical to have the precision, and we don't want to transmit any kind of torsional moment or bending moments there, then it's a very nice way to use, and it will get limited to these flexures, these members, and it just provides 6 constraints, and therefore is a equivalent to any 6 constraint kinematic joints or kinematic clamps. Yes, again here the problem could be the sheet itself, the thickness, and it's a very small, and again under compressive load it's not very good. So, one of the way is we try to reinforce the midsection, and we can get a very robust embodiment of the same thing. So, this we will be talking later when we talk about different kind of compliant mechanisms. So, here we are covering different designs and trying to show examples how these building blocks, the translation constraint and the rotational constraint can be used to design different kind of constraint devices. So, for instance, now if you want to constrain one translation and one rotation only, and suppose they are along the same axis or translation. So, again we get C1. So, along the same line. So, we constrain that translation. Of course, for the rotational constraint along the same line, we can use this building block. So, we will place the block perpendicular to that axis, and we will get the rotational constraints. So, this is rotational constraints, and this is the linear constraints, what we can call it, and we get one translation and one rotation. Of course, the 4 dots we can check, and we will be able to find, or we should be able to visualize that they are not constrained. But if we have again one translation and one rotation, but perpendicular axis, along perpendicular axis. So, this is the translation constraint, and this is your rotational constraint. So, what we realize that in this case just 2 members, 2 constraints C1 and C2 in this way is sufficient. So, sometimes we have to carefully check, and not necessarily we have to use the building block what is there for rotational constraints, although we can use it here, but it does not make sense, because just by using another linear constraint parallel to the one linear constraint here and offset and perpendicular to the rotational axis, that will provide the additional rotational constraint also. So, what if we want to have 2 translation and 1 rotation in a plane, in one plane? So, in a way trying to get a planar constraint. So, and how to get it? So, of course, along x direction we have this constraint. So, for x, what usually we can do is we can just think of this block So, what we realize that if this is the translational constraint we want, we can just put articulated link here C1. If we want to have this jet translation constraint, we can put another one here C2. But if we want to have this rotational constraint, we know that a pair, so another C3 parallel to C2 can give us the necessary constraint. But what we realize that this C1 we can achieve also by placing the diagonal constraint, and therefore, we can have C1, C2 and C3 in this fashion. So, if we have two constraints parallel and one diagonal constraint, we constrain the translation x and z and the rotation x z rotation also. And what we realize that if we are able to do that, we can simply replace this entire construction with the sheet flexure, or many times we call it leaf spring. So, this is the equivalent. So, if we just take any sheet flexures and we constrain and with the body, what we realize is equivalent to two constraint, parallel constraint and one diagonal constraint. So, it is a wave, shear wave. Shear wave provides the diagonal constraint. So, we can also compare with the parallel structure what we discussed earlier. So, like swinging gate or the bookcase where is all parallel structure, and we provide the diagonal constraint and we constrain along that plane, or we also use instead of diagonal constraint we can also use a shear plane. So, a very simple way to use a sheet flexure or leaf spring, thin sheet metal, and if we can clamp it, what we realize we can get x and z translation and also constrain the rotation along the x z plane, which is psi here. So, it provides a very good planar constraint. Yes, if you want to have just two rotation constraint, so this is one you want. So, perpendicular plane is this one. So, this will constrain this rotation. If we have this rotation, this we achieve by using this one. So, we get two rotation constraint from the two sides. So, it is a parallel configuration what we can use. So, what we see here that we are constraining two rotations and we use the intermediate body here, and we have 5 constraints here and 3 constraints here. So, it is body 2 and this is the frame. So, one DOF here. So, if we compare the intermediate body with respect to the machine frame, there is only 1 degree of freedom, which is this. And now, if we go from intermediate body to orange body, 3 constraints are there. So, there are 3 DOFs and it can move in the plane, and ultimately what we will find that the orange body with respect to the frame, it will have only 2 rotational constraints. And we can always try to find equivalent design. So, these three in a plane, so three constraints in a plane, we can always replace with the sheet flexures, and these two in a plane. So, we can always put another one with the hole, and that provides two constraints. And what we realize that this body can move along this line. So, its degree of freedom is there, but moment we connect the orange body with the again intermediate body, we see what we realize at the end, we only get the rotational constraint. Likewise, if you want to design a constraint device with the three translations. So, again suppose if it is simply x, y and z. So, along the length we can place C 1, C 2 and C 3 along perpendicular axis, and we realize that we can locate the orange body with respect to the frame, and since all three are intersecting at this point. So, this point is called pole. So, at that point is not moving. So, the position of that point on the orange body is located, but it will have all the rotations. So, three rotations, and we can also get a equivalent design. So, we can replace this one with the sheet flexure with the hole, and we can get the same thing here as well. So, if we look at these concepts closely, what we also realize that we can have a pole, or we can have an elastic joint which is not in the body, which is remotely located. So, suppose we want to have, or we want to constrain this green object with respect to the frame at a point P, then we can place three constraints in such a way that they intersect at. So, if we extend, all three will intersect at point P, and what we realize that point P is located, and in this case if we try to rotate. So, we can always have we can imagine a large body, and the point P is located there, and the green body is just part of it. So, what we realize that when we try to rotate, actually it moves on a spherical surface defined by this point P. What happens if we have three constraints on a plane? So, perpendicular to the plane, and all three are parallel, but yes offset, they are not in the same line. And if we arrange in this way, what we realize that we get this degree of freedom. So, it is all solid line. So, it can translate along x, it can translate along y, and it can also rotate along z axis. So, what exactly we got here is a mechanism to constrain a body in a planar or along a plane. So, it can move only in x y direction. So, it is like a three table. So, it can move in a plane, but if it is articulated joint, yes, it can move. What we also observe that there will be shortening effect, because if it translate in x and y, or if it has a theta motion, there will be parasitic motion in the z direction, but that is not independent motion. and that is why we always call it a parasitic motion. What we also realize that the three constraints we can also implement just by using folded sheet flexures C1, C2 and C3, and we get the same motion x, y and the rotation along z axis, which is theta. So, again it gives a planar motion, and what we realize that in many cases, suppose if you want to move a body only in a plane for and with the limited range of motion, I think this is very good example. At the same time, what we also realize that it does not go through any kind of shortening as we move along x, y and theta, and that is why wherever we want to design a compliant mechanisms and where it can move only in a plane, this is the preferred choice. So, 3 DOF and using folded sheet flexures. So, again we can constrain all the 3 rotation just using the building blocks what we covered. So, along the perpendicular plane. So, 3 perpendicular planes, if we place it, we can constrain all the 3 rotation, and what we realize that in this case the orange body can have only 3 translations. Maybe it is a good exercise to also see is there any way where we can have only 3 translations, but all the 3 rotations constrained. Can we have other configurations using only articulated links? So, again we can constrain 2 translation and 2 rotations is shown here, rotation and translation, translation and rotation, and what we realize that 2 sets can provide us that kind of motion or that kind of constraints. So, in this case what we will have is the degree of freedom will be this translation, and what we also realize that it will also have this rotation. So, this is another example. So, here instead of providing a notch or a hole at the center, we can just use a triangular piece and the hinge to the bottom, and we can get the equivalent. So, each one is replaced with this kind of flexures, and we can get the same effect. So, be aware of these things. Sometimes we are talking about DOF and sometimes constraints. So, constraint dotted line, if it is a DOF, it is a solid line. So, just check that notation, and then so we wanted to have these 2 translation in one plane, and we can use this arrangement. So, we can always cross check ourselves and see like whether this is true or is there any better way. What happens if we want to have just one translation? So, it is like a linear guidance. So, we want to move the orange object only in that direction, and we want to constrain all 5 degrees of freedom. We can place one by one, and again here we can see that yes, these 3 is like a planar constraint, and then this another 2, and but we also realize that we can always find the equivalent, and we can get a parallel guiding using the sheet flexures. Of course, for 3 we have this, and for 2C we have this arrangement. So, this leads to sheet flexures, call it SF, and this is the sheet flexure with hole. So, similarly, if we want to have just one rotation, we can again work, and we can see that again we use a 3 constraint here and the 2 constraint, and that way we are able to get one rotation only and constrain all the other 5. So, we will stop here, and we will continue in the next lecture. Thank you.